we now start?
Yeah.
Okay. So this is the second in our series of lectures on algebraic geometry for category theorists. But I also have a sort of alternate working title for the paper that I'm trying to write. And that alternate title is Doctrines of Algebraic Geometry. So perhaps like this will be the title, Doctrines of Algebraic Geometry, and then maybe that's the subtitle there or something like that. I'm not quite sure. And I think this is a good title because algebraic geometry is what we're trying to learn. But doctrines, that's really the central concept that we're trying to use in order to understand algebraic geometry. Doctrines is really what this seminar is about. And in fact, towards the end of the first lecture last week, we had our first example of a doctrine that's important in algebraic geometry. And that doctrine is the doctrine of dimensional categories. And I probably neglected to point out that it's a doctrine, that this is our first example of the doctrine. But I'm pointing it out now. The doctrine of dimensional categories. And but on the other hand, we still haven't really said what a doctrine is. So I'll try to do that a little bit right now. I'll try to say what a doctrine is, but I won't yet try to give any sort of formal, precise definition. Because there probably isn't any formal, precise definition that I know of that I'd really be happy with yet for this concept. So I'm going to leave it at an imprecise level, but I'll try to describe the concept right now. So, but in a very oversimplified way. So a doctrine is a kind of category. And when I say that it's a kind of category, I don't mean that it's an example of that kind of category. I mean that it actually is the whole kind itself, the whole class of categories of that kind. So in fact, a doctrine is more like a two-category than a category. And in the case of the doctrine of dimensional categories, we have the dimensional categories themselves, and then going between those, we have the dimensional functors, and then going between those, we have dimensional natural transformations. And these concepts, this is sort of what makes this into a two-category, the two-category of dimensional categories, or the doctrine of dimensional categories. But I guess in language of two categories, we might call this something like objects, morphisms, and two morphisms, or something like that. But in the language of doctrines, it's very convenient to refer to these things as the theories. So an individual dimensional category, that's a theory of the doctrine of dimensional categories. And then the next thing, the dimensional functors, those would be what you would, in the language of doctrines, those would be what you would call interpretations, or sometimes they're also called models. Interpretations between theories. That's what the dimensional functors between the dimensional categories are. And then there's a third level down here, and I guess I'll just call that the morphisms of interpretations, or perhaps the morphisms of models. And this pattern and this language is something that we use talking about pretty much talking about any doctrine. And this language will be important in understanding our big slogan that I introduced last time, which was that every space, and perhaps I should begin to qualify this a little bit now. I'm going to mean like every space of the kind that algebraic geometers study. Every space is a moduli space of models of a theory of a doctrine. And then there's a little bit more to the slogan. It says, and to understand algebraic geometry, the key to understanding algebraic geometry is to identify and understand the doctrines that are involved in algebraic geometry. And that's kind of what we're trying to do here. So this is our first and probably simplest example of a doctrine that's important in algebraic geometry. And it's important in this way. It's important in this way, that you use this idea embodied in this slogan in connection with this doctrine in particular, but also other doctrines that we'll study. So there's still lots more explaining to do about how to understand all this, but we'll hopefully get to that. So,
is there some fixed sort of codaline-ish type of space?
That's a very interesting question. Interpretations suggest that you want to have a particular, sometimes I call it an environment. A theory is like a thing that gets interpreted, but it wants to be interpreted into something else. And that something else, you can call it something else a theory too, but sometimes I like to call it an environment instead. So like theory in this context is almost a word for domain, and environment is almost a word for codomain. And Alex is suggesting that maybe there are particular environments that are considered very important to interpret your theories into. And that's absolutely true, and we'll get to that pretty soon, hopefully.
And
yeah.
The moduli space part of that slogan, is that somehow related to the morphisms of models?
Yes, and in particular the isomorphisms. Moduli space, naively at least, suggests the idea of modding out by isomorphisms, counting models as giving the same point in the moduli space if they are isomorphic, if there's an isomorphism between them. And so that's some general information about doctrine. But now I really want to talk about dimensional categories. And we've got this word dimensional that keeps on showing up here. And we've talked a bit about how the reason that word dimensional is there is because this whole doctrine of dimensional categories is really a formalization of the subject of dimensional analysis. And so we've talked about this. We've talked about how in dimensional analysis you study dimensions, things like, so this kind of dimensional analysis is the kind of dimensional analysis that, for example, you learn about in high school physics. So like in high school physics, you learn about dimensions like length and time and energy and momentum, and velocity and mass. So you have dimensions and then you have quantities that live in those dimensions. And that's what dimensional analysis studies. But we talked about how there's really a nice surprise in that this whole doctrine of dimensional categories, it lives a double life. It lives a double life because besides the study of dimensions and quantities, there's the study of projective varieties in algebraic geometry and generalizations of projective varieties. And in the study of those things, you study line bundles, and line bundles that live over the projective variety, and you study sections of line bundles. And perhaps surprisingly, it turns out that there's a sort of cryptomorphism, so-called cryptomorphism, a sort of secret correspondence that says that dimensions and line bundles are really secretly the same thing. And quantities that live in those dimensions are really secretly the same thing as sections of line bundles. And this idea of a cryptomorphism, a secret correspondence, it's a good thing to be able to understand and exploit. Because to the initiated, who know the secret, who know the secret correspondence, it gives you a sort of two for the price of one effect. You just have to study one subject, dimensional analysis, say, and along for the ride comes this other subject that's secretly equivalent to the study of line bundles and sections of line bundles over projective varieties and generalized projective varieties. And so we'll be talking more about this. We'll be talking more about dimensional analysis from the point of view of this doctrine of dimensional categories. But I want to mention a curious incident that happened some years ago. A mathematician by the name of Lila Schnaps, a European mathematician, and so I'm not really too sure on how to pronounce her name, but I'll call her Lila Schnaps. She was traveling through Europe, and she stumbled across, or perhaps deliberately stumbled across, the place in Europe where Alexander Grothendieck was living at the time. And Grothendieck was a profoundly influential mathematician back in the 1950s and 1960s in particular, and in particular in the area of algebraic geometry, profoundly influential. But at some point after that, he became very difficult to find, very difficult to get hold of. And perhaps this was due to some dissatisfaction of his with some part of the mathematical community or some part of the world at large, not really sure. But he became very difficult to find. Although I could have sworn that I saw him sitting on a bench on University Avenue. And he became very difficult to find, but Lila Schnaps found him. And Lila Schnaps is not only a mathematician, she is a mathematician whose work has been greatly inspired by the beautiful ideas of Alexander Grothendieck in algebraic geometry and other areas. And so here was an opportunity for her to meet her idol. And she even, it almost turned into an opportunity for her to seriously discuss mathematics with Grothendieck and work with him. But as they talked and as they met several times, it became clear that Grothendieck was sort of throwing various sort of roadblocks into the way of the possibility of having serious discussions. And he sort of issued a challenge to Lila Schnaps. He asked her a question, and he suggested that if she could answer this one question, then he would be willing to seriously discuss mathematics with her. And the one question was, what is a meter? what is a meter? Now that might be a peculiar sounding question, and it probably is a peculiar question. And if you read up on this incident, you'll find that there's some more information available to suggest what it was, perhaps, that Gurdjieff was thinking about when he asked this question. Apparently, he's thinking about physics, thinking about units of measurement. Apparently, he had some concern with the speed of light, which is measured perhaps in meters per second. And when I first started to really seriously learn algebraic geometry recently, I had heard about this incident before. But after I seriously began to learn some algebraic geometry, I became more interested in this question. Because Grothendieck's preoccupation with units of measurement really reminded me of my own preoccupation with units of measurement. I mean, this whole subject of dimensional analysis, when you study dimensions and quantities that live in those dimensions, the dimension that a quantity lives in, that's really closely related to what's the unit of measurement that you use to measure that quantity. And so I even have a sort of answer to Grothendieck's question. My answer is something like a meter is some kind of section of a line bundle, or something like that. I don't really have the details completely worked out yet, but it's something like that. And
Well, if you watch movies on the internet.
yeah, so I'm actually kind of hoping that Grothendieck is somewhere right now watching this video, and he's saying, yeah, that's the answer. That's the correct answer. and I'm hoping to get something out of this. I'm hoping maybe that'll find me one of those coffee drinks.
A mocha loca?
Yeah. Although,
Good, ask him when he's on.
well, I mean, perhaps you won't get one, because when I saw him last week, yeah, he asked me for a quarter.
You need to buy him a mocha loca.
I guess. I mean, but if Grothendieck will send me an email or a text message or something,
Or a video posted randomly online,
sure,
just like this one.
then if that would happen, then I think we could really get to the bottom of this meter business once and for all. So I'd like to get back to our specific example of a dimensional category that we introduced towards the end of the first lecture last time. So let me try and do that now. So, our example last time, it was supposed to have a sort of high school physics flavor to it, in some sense. Involved concepts like conservation of momentum and conservation of energy. And I'll try again now to write down a description of the dimensional category that we use to describe this situation. So, I'll draw a sort of grid here. So you might remember that dimensional category, you can also think of it as a graded commutative algebra, graded by an abelian group of so-called dimensions. And that's what this grid that I'm trying to draw here is supposed to be. It's supposed to be this abelian group of dimensions. And in our particular example, it's supposed to be z squared. So this, two-dimensional grid, that's about what you expect with a picture of z squared. So it's an abelian group, so it's got an identity element, which I guess will be right here. So the identity element of the dimensions, that's the dimensionless dimension. So that's the identity element right there. And then I think we had, I'm trying to remember which axis we used for which one. We have a mass axis and a velocity axis. Is there any preference? I can't really remember. Let's see. I guess it should be like this. Mass dimension, this right there. So for example, mass squared, over here, mass cubed, etc. A velocity dimension is right over here. And momentum, that's the mass dimension times the velocity dimension. So the momentum dimension that's right here. And then the energy dimension is mass times velocity squared. So velocity squared would be right down here. And mass is right there, so energy is right here. And then we have some generators and some relations. And we can display in this grid where the generators live and where the relations live. So the generators, we have some generating masses and some generating velocities. So we have two particles. That's the idea for our situation. So we have the mass of particle A and the mass of particle B. And then we measure their velocities at two different times. So that gives us 4 velocity quantities. That's 4 generators in the velocity dimension. And I think I called those something like V1 sub A and V2 sub A and V1 sub B and V2 sub B. And that's all the generators. Then we have some relations. So in the momentum dimension, we have a relation which says what? That the starting momentum, which is the mass of particle A times the starting velocity of particle A, plus the mass of particle B times the starting velocity of particle B, is equal to the final momentum. So it's the mass of particle A times the final velocity of particle A plus the mass of particle B times the final velocity of particle B. And conservation of energy is similar, except that the formula for energy involves velocity squared. And I think it's also recommended that we should put factors of 1/2 here. So maybe, but the factor of 1/2 is going to be on both sides of the equation, so it doesn't really matter. So I'll leave the 1/2 out. So mass of particle A times the starting velocity of particle A squared plus the mass of particle B times the starting velocity of particle B squared is equal to the mass of particle A times the final velocity of particle A squared plus the mass of particle B times the final velocity of particle B squared. So this is a presentation of a graded commutative algebra graded by the abelian group. But the fundamental theorem of dimensional algebras and dimensional categories says that this is really a so-called dimensional category. So the objects are these squares in the grid, and the tensor product of these objects is really just this abelian group operation, which which I guess we'll call multiplication. It's like mass times velocity equals mass times velocity, also known as momentum. So, let's try to think about how this is supposed to exemplify the use of doctrines in algebraic geometry. So, we have the moduli space of models of this theory. Well, that's what we have. That's how we get a space from this situation, from this dimensional category. It's the moduli space of models of this theory. So, or models, the interpretations of this theory. The interpretations of this theory into a standard environment, as Alex was alluding to. So I guess that's really the first thing maybe that we should think about is what's going to be our standard environment that we're going to interpret this theory into. So, I call it an environment, but you have to remember an environment is really just another theory. And in this, so what is a theory? So a theory is a dimensional category. So we need some other dimensional category to interpret this dimensional category. And the sort of standard example of a dimensional category that's good to use as the environment to interpret your theories into it is the dimensional category of lines over your favorite field. So I'm not quite sure what your favorite field is. Maybe your favorite field is the real numbers, or maybe it's the complex numbers, or maybe it's even something different than that. In fact, let's just think about that for a second. Let's think about the use of the choice of the real numbers, field of real numbers, or the field of complex numbers in this context, in this example. Algebraic geometry really tells us that we have somewhat of a free choice. You can have your own taste about what your favorite field is, and in fact, it's actually better sometimes to have somewhat eclectic taste and to sort of like all different fields at the same time. But on the other hand, the complex field, there are some very nice things about the complex field. A lot of algebraic geometry really like using the complex numbers. The field of complex numbers has some very nice properties like being algebraically closed and things like that. But there's even more nice things than that. It is a complex algebraic geometry ends up being related to things like complex differential geometry, where there are always notions like holomorphic line bundles and holomorphic sections of line bundles, and that's directly related to all the line bundles and sections stuff that we'll be doing. So there are good reasons why it's sometimes good to think about this example, for example, in the context of working over the complex numbers and using this dimensional category as the environment where you interpret the theory. But on the other hand, our whole concept of measurement, which is what dimensional analysis is all about, that's very tightly tied in with our whole idea of the field of real numbers. So there's also a good philosophical argument that it would be interesting to consider examples like this example in the context where you think about your favorite field as being the field of real numbers. And in fact, there's probably all sorts of extra special things that should happen when you take into account the special nature of the real field. How measurements certain kinds of measurements tend to be positive, things like that. So there's probably all sorts of extra details to the story that would be fun to think about, but we're not really going to think about them at this moment. In a way, we're really trying to take a somewhat abstract algebraic geometry viewpoint towards this example. Because that's what we're trying to learn, algebraic geometry. So I said, I put in quotation marks, the category of lines over your favorite field. All I really mean there is one-dimensional vector spaces. That's what I mean by a line, a one-dimensional vector space. And if you think about that, that's a dimensional category. Because again, the whole idea of a dimensional category, the objects are dimensions, but a dimension and a line are kind of the same thing, right? I mean, a line is a one-dimensional object. One-dimensional object, that's kind of like a dimension. So, in fact, this is somewhat of an answer to Alex's question about what environment we're going to interpret our theory to. But it's also an answer to a question that John Werder asked about last time, when he was trying to compare what we're doing here to affine algebraic geometry, where instead of having a graded commutative algebra, you have a commutative algebra, ungraded, and you take homomorphisms from that commutative algebra into your base field. And John was asking, well, what's the analog of that? Or do we have anything like that here? And yes, we do. And this is the analog of it. So instead of having homomorphisms from your ungraded commutative algebra into your favorite field, we're having interpretations from your graded commutative algebra into really, it really amounts to, I guess, thinking of your. There's a way to think of this. This is a dimensional category, so there's a way to think about it as a graded commutative algebra. But in any case, this is the analog. This is the thing that gives you the points. Just like in affine algebraic geometry, you get the points by taking homomorphisms from your commutative algebra into base field. And but there are extra subtleties in this case, because in the affine case, you just took those homomorphisms and it just gives you a set of points. But in this context, we are harming a category into another category. We're harming a dimensional category, which is our theory, into another dimensional category, which is our environment. But when you harm a category into another category, you get a category of such things, of such functors, really. In this case, dimensional functors. And then you need to mod out by the dimensional natural isomorphisms. And so that's an aspect of what's going on here. So a point in our space is basically a model of our theory. Except perhaps more precisely, it's an isomorphism class of model theory. So we have to think about that isomorphism class aspect as well. So let's think about what a point is. Let's think about what a model is here. So a model is this kind of thing. It's an interpretation of this dimensional category into this dimensional category. So it's, in other words, each square in the grid over here is an abstract line in our theory. And an interpretation of this, a model of this theory, it involves a realization of these abstract lines as concrete lines, actual lines over your favorite field, over, let's say, the complex numbers. And so let's try to demonstrate a little bit how this works. So there are two generating dimensions here, the mass dimension and the velocity dimension. So mostly you just have to worry about how to interpret those two dimensions, and then all the other dimensions will go along with the ride. But then you also have to interpret the quantities that live in the dimensions, so the generators and the relations. You have to think about the generators and the relations. But so we're going to interpret these two abstract lines as being specific concrete lines.
So the zero-dimensional category means that also zero-dimensional vector spaces?
Say that again?
You need zero lines and zero dimensions?
No.
What about this? That's this picture.
I guess it's not what you're expecting. We're talking about tensor product of line bundles, which is, yeah, I mean, it's like, can someone describe it geometrically what the inverse, so it turns out line bundles with respect to tensor products really do have inverses. I mean, if you're used to think of like maybe you could, like, for example, get tensor product mixed up with direct sum or something like that. If anybody told you that direct sum, that something had an inverse with respect to direct sum, that would be a very peculiar idea. It doesn't really make sense. But with respect to tensor product, there's really no reason why you can't have an inverse. Now, if somebody told you that a higher dimensional vector bundle had an inverse with respect to tensor product, then that would be a peculiar idea, because that would suggest that the inverse had to have a fractional dimension or something like that. But if you have a one-dimensional vector bundle, a line bundle, then there's really no reason why you can't have an inverse for it. And in fact, we do have inverses for these. So,
I think I was just worrying about the emptiness of those squares over there.
Okay.
They're empty in some way, but you were saying that maybe they have to be zero-dimensional, but that's not the right.
Okay. Okay. Well, so one of the things, okay, there's lots of possible confusions here. And perhaps one of the confusions that Alex is sort of pointing at here is that this word dimension can mean a lot of different things in this context. So each one of these grids is a dimension. It's a line bundle. But in addition, there are all sorts of interesting questions that you can ask about these dimensions. You can, I don't want to say this. You can ask what dimension each dimension is. There are sections that live in each dimension, and it's a vector space of sections in each dimension. You can ask for the dimension of that vector space. You can tell that there's going to be a one-dimensional vector space here. Well, I'm not sure how it is, but there is a one-dimensional vector space here because you have the identity element of the great commutative algebra lives there. And then over here, you can see that there's sort of two dimensions. I mean, there's two generators. Now, if you think about it, there's no relations that are going to disturb those generators. And then, and a lot of these other dimensions of these dimensions, don't say that. Okay.
Dimensions of
The dimensions of these grades, yeah. This one, to keep the calculator, this one is 3. This one has 4 generators here, so there should be like 4 here. Sorry, I didn't mean enough room to really write the numbers in here. There's going to be 4 here, 2 here, 1 here. Now, if there's 2 here and there's 4 here, you can multiply those two together to get 8 different quantities, 8 different linearly independent quantities that live in this dimension. Sorry, I say linearly independent? That's the problem. They're not quite linearly independent. They would be linearly independent if you didn't have this conservation of momentum relation. But that's a single relation, so it cuts things down to just 7 dimensions. There's actually going to be a 7-dimensional space of sections here. And there are some general methods that you can use to calculate these dimensions. That's one of the minor things that algebraic calculators know how to do pretty easily, is calculate a lot of the dimensions of these vector spaces of sections. But I just want to point this out now just to try, perhaps by focusing on it, to try to dispel this possible confusion between.
So like what's that one?
Yeah, I mean, look, there are just no, all of these are going to have empty, these are going to have 0-dimensional spaces of sections. But that doesn't change the fact that they still are dimensions. In the dimensional category that we're studying, they are still one-dimensional objects. The fact that they have 0-dimensional spaces of sections, that's a separate question. It can be confusingly similar sounding, but it's actually a very different question. So we'll have to try to keep those. We'll have to try to avoid getting those kind of things confused with each other. So, so we're thinking about what is a realization of this theory. So one of the slightly peculiar things about realizing this theory is you have to realize each abstract dimension as a concrete dimension over here. But when you look at what the concrete dimensions are over in this environment, in some sense, there's not a whole lot of choice about what the concrete realization is going to be. Because, I mean, perhaps there are many different one-dimensional vector spaces over your favorite field, but they all look the same. There might as well just be one. Once you've seen one-dimensional vector space, you've pretty much seen them all. So it's really not an interesting choice as to which one-dimensional vector space you're going to realize your abstract dimension as. You might as well realize it as the standard one-dimensional vector space. And once you do that, that means that when you realize these quantities, those are really just getting realized, the quantities are really just getting realized as elements of your standard one-dimensional vector space. And elements of your standard one-dimensional vector space, those are really just elements of your field. The one-dimensional vector space is your field. So really, if you think of what's going on here, this is really just a homomorphism of graded commutative algebras into your favorite field. Well, it depends on what I'm not sure exactly what the standard definition of homomorphism of graded commutative algebra is when the two algebras have different grading groups. So this algebra has z squared as its grading group. Over here, we're really taking one single line. So it's really just, it's graded by the trivial group. So
it seems like there's zillions of lines, so it's graded by this
enormous
group. But that's equivalent to a category where all lines are equal.
That's right. And you can get away with reducing it to just having one single line. And so you're just really studying a graded commutative algebra, but that's trivially graded. But it's still meaningful to talk about the homomorphism being graded. So that's concretely what you can think of the models as being in this situation. So it really is a lot like the way John Porter described what happens in affine algebraic geometry. But instead of having just homomorphism of ungraded commutative rings, we have some sort of homomorphism of graded commutative rings. Except, wait a minute. If this is trivially graded, then maybe the respecting of the grading is actually trivial. Is that right?
Yeah.
Yeah. Okay. So
also says that you were making it concrete, but in this particular example, or even lots of examples, like if you could make it even more concrete, what such a homomorphism graded commutative algebra amounts to.
But what do you mean? So that you're specifying numbers for
Yeah, you didn't say the word number, yeah.
I think I sort of did.
Well, you said no.
Okay, so yeah, you realize these quantities as actual numbers. An abstract quantity wants to be, in a specific model of the theory, it wants to be a number, and that's what you do. But the numbers you pick have to satisfy these equations. They have to obey the constraints, the relations. They have to obey conservation of momentum and conservation of energy. So that's what the models are like. That's what the realizations or interpretations of the theory are like. But then you have to take the moduli space. You have to mod out by isomorphisms of models. So you have to think about what isomorphisms of models are really like. And I guess that ends up being, that's the dimensional natural isomorphisms between the dimensional functors. Again, these models that we were just talking about, those are the dimensional functors. Now we're thinking about the dimensional natural isomorphisms between them. And you can think about what those mean. You know, you can do it in a very careful way, but I'm not doing it in a very careful way now. I'm trying to describe it in a somewhat intuitive, physical way, which is that you have these independent dimensions of mass and velocity, and basically you can independently rescale. You can rescale these dimensions independently. And that's the amount of freedom that you have in having superficially different looking models that are actually equivalent to each other. They're actually isomorphic models. Because there's no absolute scale. I mean, but that's, but the exact about the meter. But there's no absolute scale of mass. You have to pick some unit of measurement or something like that. And it's kind of arbitrary what unit of measurement that you pick for measuring mass. And changing your mind about that arbitrary unit of measurement is rescaling this abstract dimension of mass. And similarly, the velocity dimension can be rescaled. Yeah.
Can you just get me back on track with what the objects in this category are?
They are these squares in the grid. They are these dimensions. Like mass is an object. Velocity or momentum. These are objects in our category.
And so I want to understand, given one of these squares, what kind of things in this way, that dimensional natural transformation is. That's where
Okay, let me try and say a little bit of that. So, see, in this example, we have velocity as a primitive dimension. But let me just mention that in some theories, velocity is not a primitive dimension. Velocity is like distance divided by time. All right. So velocity is distance divided by time, which you might measure in like miles per hour or something like that. So if you have a quantity like 50 miles per hour or something like that, you can think of that as a quantity that lives in the velocity dimension. But you could also think of it as a morphism from hours to miles. That's what, you're driving 50 miles an hour, you're turning time into distance. It's a morphism from the time dimension to the distance dimension. So that's just kind of a reminder of how to think about these quantities as also being morphisms between different dimensions. And the numerator, you can think of whenever you can express it as a numerator over a denominator in different ways. And every time you express it that way, you're giving a different way to think of that as a morphism. Now, what question was I trying to answer?
Yeah, so that's a little bit of it, but then, so given an object in a dimensional natural transformation,
so let's see. So what does the dimensional natural isomorphism do? It assigns to each object an isomorphism between the functor values.
right, so between two lines.
Which happen to be the same line. So it's the same line. So it's really assigning an endomorphism, or in fact, an orthomorphism. It's assigning an orthomorphism of the standard line. And an orthomorphism of the standard line is just a scalar. So that's what I mean when I say that this natural isomorphism is just rescaling. It's a scalar that's rescaling the dimension. It's vertical scale.
I thought you were doing it by taking MA and B specifically, like rescale. This will then rescale this.
Yeah, it sort of automatically does. I mean, so you could have one model where like the mass of this was 10 and the mass of this was 20. But that could be equivalent. It would be equivalent to some model which is 100 and this is 200. It's the same model. You're just measuring it in different units of measurement. So this rescaling that we're doing here, this is what shows up in algebraic geometry as the fact that you're doing projective geometry rather than affine geometry. So projective geometry is where you mod out by rescaling. You mod out by scalars. Let me just draw one simple example of that. I'll draw a little bit of a picture of the projective line. So the projective line is really lines in a two-dimensional vector space. So we have the flat plane as a two-dimensional vector space, and there's all these lines through the origin. And that's sort of the points of the projective line. So it sort of looks like this. etc. And so you can think of the points of the projective line as really being the points of the point of the plane, the flat affine plane, with this rescaling ability. And so, you know, all the points on this line, they all count as the same point, except there's one little tiny thing you have to worry about, which is that point in the middle that's on all of the lines. Or perhaps, depending on how you think of it, you might think that it's not on any of the lines. And I guess depending on how you define what a line is. And so algebraic geometers, they really have to get rid of that point in the middle. They sort of call it the irrelevant point. But in our formalism, it's not really being gotten rid of. It's really, so far, it would be, in the doctrine that we're using so far, there's nothing really that gets rid of the irrelevant point, the irrelevant point that algebraic geometers don't like. So, you know, it might be nice if we had a more powerful doctrine in which you could express the idea that you want to get rid of this so-called irrelevant point. So that's something that we may get to at some point. But there's also another attitude you can take about this point right in the middle of the plane that algebraic geometers get rid of when they're creating the projective line. See, we're modeling out by rescaling here. Again, this idea of dimensional analysis. Modeling out by scalars, or by rescaling. Another name for rescaling in physics is it's also sometimes called renormalization. And this is sort of a picture of the action of the renormalization group, so-called renormalization group. I mean, it's a simple example of a renormalization group. Because this probably wasn't called as an example, but it is. This is a renormalization group. And right in the middle is sort of a fixed point of the renormalization group. And physicists know that fixed points of renormalization groups are actually a very important, interesting thing to study. So the idea of calling this the irrelevant point is arguable. Perhaps I'm sort of using that as an excuse for why our formalism doesn't really get rid of this irrelevant point. But later on we'll develop techniques for having more latitude, either to include the irrelevant point or to exclude it. And those techniques will involve going to more powerful doctrines, more expressive doctrines, in which you can say more things. You can have more control over the spaces that you're creating. And so the projective line over here, this is actually a second example. Perhaps I should try and formally introduce this as another example in one. But let me say a little bit more about this example over here. So, so what time is it?
3:12.
Oh, okay. I'm sorry, I didn't know that. Okay, I'll try to finish up now then. So.
Yeah, you have 18 minutes.
That's the second?
Yes, it's 3:30.
It is at 3:30. Okay.
So you should try to finish up now.
Okay. Okay. So,
Looking at a non-existent
yeah, you had something written over there for it.
That was from last time.
Oh, that was from last time. Oh, okay.
I'll write it up again when you really have.
Okay. I was losing track of time here. Okay. So yeah, perhaps I'll get to this as a second example in a moment. But let me say a little bit more about this example that we're doing here. So, well, there are lots of nice little fun educational things that you can do with this example to try to learn some of the very elementary aspects of algebraic geometry. You can try and think about what the moduli space of models of this theory really is like. And it's not that hard to come up with there are probably very easy systematic ways of figuring things out about this moduli space. There's systematic ways that algebraic geometry would know about. But even if you don't do it systematically, it's pretty easy to guess various things about what this moduli space is like. And so, for example, let's try to so a really gross coarse thing to know about a space is what dimension is that space. So let's try to figure out what dimension this space is. So I think it's pretty intuitive that calculating the dimension of space is going to have a lot to do with, calculating the dimension of space has to do with sort of like counting the degrees of freedom that there is that a model has. In creating a model, how many degrees of freedom do you have? So generators are giving you like degrees of freedom. But relators are giving you negative degrees of freedom, degrees of constraint. Cancel out degrees of freedom. And but there's something else that's also contributing to dimensions. The dimension of this, right, here's another sense in which some concept of dimension is showing up here. So there are many different concepts of dimension floating around here, which are important to not get too badly confused with each other. So the dimension of the moduli space in this example,
Should you ask poll people what is it?
Okay.
What is the dimension that you're trying to calculate? The moduli space?
The dimension of the moduli space, the degrees of freedom that you have in constructing a model, and only the degrees that actually give you non-isomorphic models, only those are important. So right there, I just gave a clue about how to calculate the dimension. So, anybody have any ideas? Vote for what number? 3 dimensions? Okay, any other votes? Can you say how you got 3? Yeah?
You should make everybody vote.
Okay, you have to vote. You have to make up the number.
I vote 3.
3? Okay.
No, it's just a big one.
And what is the common order of vote?
I'm going to go 2.
2. Okay. Can you try to give an argument for why you think there are 2 dimensions?
There's 6 dimensions.
6 generators
Right.
give us
6
degrees of freedom, 6 dimensions to start with. So that's a starting point, 6 dimensions. Yeah.
Each relation kills 2 dimensions.
I agree. So
Each relation kills 2.
Each relation kills 1 dimension.
That's
So,
one. Okay.
so total you kill 2. So that's down to 4.
Yeah. So we're down to 4 from. We start out with 6. Now we're down to 4.
And we can rescale each of our 2 kinds of basic units. So
Right.
that kills 2 more.
That's right. So the rescaling, the ability to rescale this dimension and to independently rescale the velocity dimension, that's a kind of gauge freedom or something like that. If you want to use something that I don't really know what it means. And that gauge freedom is kind of illusory freedom. So it's kind of telling us that you have to subtract that illusory freedom away from the nominal freedom that you had to figure the actual true degrees of freedom. So John is correct, I think. If I didn't screw up, this really does give us a 2-dimensional moduli space, 2 degrees of freedom in the moduli space. And so again, there's all sorts of educational things that you can do with this example. So like, we're getting a 2-dimensional moduli space here. That's also sometimes called a surface. And the algebraic geometers tend to call it a 2-dimensional thing. They call it a surface pretty much regardless of what the base field that you're working over is. Even if your base field is itself like 2-dimensional, so they might think a 2-dimensional complex object is really going to be 4-dimensional, 4 real dimensions. But algebraic geometers still think of it as a 2-dimensional object, and they still call it a surface. And so the point is that this is actually giving us a surface here. And algebraic geometers know a lot about surfaces. They have some sort of classification of surfaces. And so you could ask, how does this particular space fit into the algebraic geometry's classification of surfaces? And I'm sure it fits in some very simple way. This is not a very complicated. It's not a very complicated surface at all. It really might be a very trivial example of a surface. I'm not sure exactly how trivial it is. If you think about what's going on here, you can sort of forget the velocity dimension and just think about the mass dimension. And that amounts to taking your moduli space and projecting it onto, really just onto the projective line. If you think about this thing up here, it's really just a projective line. It's like, this is a two-dimensional vector space and you're modeling out by rescaling. So it's really this picture over here. So that's saying that this moduli space is projecting onto the projective line. So what you've got is a surface that really consists of a one-dimensional space, a curve, together with some one-dimensional bundle over it. So it's like a bundle of curves over a curve, and that's a particular type of surface. And I think in the algebraic geometry classification of surfaces, that's a really, that's really one of the simplest examples of surfaces. And this is even one of the simplest examples of those. So I think it's a curve over the projective line, and the fibers are themselves very simple curves. So this is a very simple example of the surface. But still, there are educational activities that you can do with this example to try to learn some of the things that algebraic geometers know how to do. So, for example, you can try and learn some systematic methods for calculating the number of sections, the dimension of the space of sections, the number of linearly independent sections of each of these different line bundles. That's another activity you can get involved in, do things like that. So, how much time left? Oh, it's 5 minutes. So, well, I mentioned that I'd actually like to do the example of the projective line here. This is supposed to be a picture of the projective line. And I actually even mentioned that if you take this example here and just consider this part of it, then you're actually getting the projective line. So now that I've changed the picture a bit, this is actually a depiction of a bunch of line bundles over the projective line. And these numbers here are telling us the number of sections. It kind of keeps on going like this, very simple pattern. 4 is the next one, etc. All the way beyond this point, I think we already alluded to in trying to answer Alice's question. There's 0 dimensions. 0 is the number of dimensions. But 0 is the number of linearly independent sections. So this is the projective line. This is a way of thinking about the projective line in algebraic geometry. So let's try to think of the projective line as a moduli space of models of some particular theory. So let me try to take this dimensional category that's described right here, which gives us the projective line as the moduli space. Modulo is a technicality, so modulo the technicality of worrying about this irrelevant point over here. This dimensional category gives us the projective line. Let's try to think of this dimensional category. Try to think of this moduli space. Let's try to verbally describe what is the theory, this moduli space we're looking at here. So let me try to write a verbal description of this theory. It's the theory of one line object L equipped with a linear mapping to standard two-dimensional space. To understand how this verbal description is a verbal translation of this thing, well, you really have to think about these two free generators here.
Well, it takes two numbers to say how you're linearly mapping a line into two.
Yeah. You've got a one-dimensional vector space here, and you're mapping it into standard two-dimensional space. So it's like the field, let's call it F squared. That's a standard two-dimensional space. So you've got a linear operator going from here to here. So this is sort of like a little 1x2 matrix. A little 1x2 matrix. Right? I mean, you have a linear map from L to F, and another one from L to F. And so these are really linear functionals on L. So if you think about that, that's sections of the dual line bundle. So I think what we're saying is that this one over here is really L. And this is the dual line bundle, which you think was the inverse of L. And we're saying that it's got two sections. These two linear functions on L, those are sections of L dual, L inverse.
Or elements, so
Yes. I mean, you have to remember, a bundle is just a varying thing. So a section of a bundle is really just a varying element. So you call it an element. I mean, the philosophy that says you should usually leave out the word bundle. Because bundle just means that you have a varying thing, a parameterized thing. And since everything in the world is really parameterized, you shouldn't even mention the fact that it's variable, it's parameterized. Take for granted that everything in the world depends on extra parameters that we don't even talk about most of the time. So we'll have to try to explain this better later. But this is an attempt to verbally translate this theory.
And that picture is clearly a picture of the moduli space. There are all the mappings from L and F squared.
Yeah, and there is this extra thing. Yeah, I mean, we would really like to say that it's not just a linear mapping. We'd like to say that it's a linear embedding. That would be better. That would really give us the moduli space not allowing this extra point, right? Because there's this very degenerate map you get by having the zero linear functional there and the zero linear functional there. And that's that weird point that we don't really want. The point that the algebraic geometry is deemed the irrelevant point. So we would really like to have our language be able to express the idea that we want a linear embedding. So when you take the moduli space of this theory, you really look at exactly the projective line. So that's one of the things we're aiming towards being able to get. But for now, we're sort of stuck with this situation where we just have the moduli space of this theory, which is kind of what's expressed in here. So we'll go ahead and quit here, and we'll try to do a better job of explaining all the things that we're screwing up. Okay.